So let's start this talk. Thank you for attending. So I'm a researcher and I teach distributed systems mainly in Min University, and we do research in the context of this lab, the HAS lab, the High Assurance Software Lab. And so my proposal is to try to explain you that causality is simple. And I've chosen this title, but when I was doing the slides and looking at the content, I had to do a little rewrite, okay? So it's going to be moderately simple, but I'll try to make it as intuitive as possible, okay? That's the overall goal of the talk. So let's start with that. And why should we care about causality nowadays? Basically, we should care because it's very hard nowadays to program and not be programming in the context of a distributed system, okay? So what used to be a playground for academic researchers that were doing very nice algorithms and using nice math to impress each other, now some of these things are really used nowadays, and when they are not used, some anomalies occur in the systems that we run, okay? So it's important to try to work with them, or at least use libraries that implement these structures and know when we need to use them. So let's get into that. Some of the anomalies that you might have experienced, I have some examples here. So suppose you didn't, well, the sound of your telephone is probably off, but you can feel a buzz. So you get a notification from Twitter that there is a new interesting tweet that you should go and check. And you could go and check it, but it's not there yet. So something strange happened. What happened here is that we had two different notification channels. One did a notification that something was available, but it's still not cached locally on your local content provider for the application. So you get a miss when you go and fetch the tweet that you are interested in. So this is something that could be prevented if there was a causal delivery precondition between the two events. Another example, which is a classic one, is that you want to post, say, some picture of you in vacations when you were supposed to be working or something like that. So you remove your boss from the list of people that are going to see pictures in that group. Then you post to the group, but then he sees the posting. So what happened is that there is a relation between the two events that was not enforced by the system. And he was allowed to see the picture before the removal got into effect in the system and he was removed. On another area, if you use systems based on last writer wins, like Cassandra, other types of anomalies also can happen. So this used to happen. I don't know if this has been fixed nowadays, but the following thing could happen, that you could write into an object in Cassandra, and if your clock was far ahead of all the other clocks that are using it, you actually are writing that with a tombstone. And this means that other users will be able to read what you have written, and when they try to write back, like a response, they will not be able to do it because their time is behind the time of the timestamp that was used for the first writing. So there's lots of problems with using clocks. And other sort of inconsistencies, like, for instance, some tweet was favorited 3 times, but only 2 are over there, okay? So now you could think, can't we use timestamps to fix it, or simply use a spanner and solve these issues? Well, I'm going to spend some slides here trying to show you about some of the limitations of real time. So even if we were able to have a perfect coordinated time everywhere, we will still miss some information. So the problem with time is that there is no now. And I'm referencing this to a very nice article by Justin Chi that appeared in ACMQ last year that talks about these kind of problems. So basically, we have a now because we are in the same room, and we might have more or less the same time reference. But this thing doesn't translate to what is happening in other locations in general. So, for instance, when everyone knows this, that when we are looking at distant events, like I think this is the Crab Nebula, we are actually looking at the past. So the more distant something is, the more into the past we are looking. And this is quite obvious in astronomy, but this thing also happens in our world. So if I'm receiving a message that is coming from Australia, there is some milliseconds of delay in relation to the time where that event occurred. And actually, light speed is the speed of causality, okay? So we need to use causality to track the relations between events, even in the real world. So basically, time is inherently local. So time can be very useful. If I have a wall clock that is close to me, and if this wall clock is growing monotonically, I can use this wall clock to do useful things. And I might even not try to use some approximation of time. I can do very useful things just by having a counter that starts at 1, and then I keep incrementing it as I need another reference to time. But what will be tricky will be trying to use information from wall clocks at very different locations, okay? Because we'll have different delays, and it's really hard to relate events that occur in multiple locations in terms of what will be real time. Final thing about time, before I get into the causality tracking, is that in order to track time, we need memory. We need to have memory of what happened. If you look at this image on the left, and now this is before, and this is after. You noticed a transition. But if you actually look at the same thing, and you consider that one before, you see the same transition, and they are the same image. So this is showing that some events in the world, inherently, they don't have any notion of time. So if we looked at the two pictures, we have no idea of knowing which came before the other. We only know that smoke is flowing in a given direction at this scale because we have this persistent memory in our eyes and brain of what we have seen before. And this is what we need to do also in distributed systems, because we have many states that are indistinguishable. So in order to relate them, we need to have some notion of memory. So we need to basically memorize events. So the overall motivation is that time is complicated. It's not a straight timeline. What we are really looking at in distributed systems is that a web of causes and effects that we need to be aware of in order to make sensible decisions. So I'm going to cite a paper from the 70s, very well-known one, from Leslie Lamport, which is a physicist and that recently won a Turing Award. And he basically realized or translated these notions from physics into distributed systems and introduced the notion of causality to the field of distributed systems in the late 70s. So in order to introduce it, I prepared a simple social interaction example to explain it a little bit, and then we'll get into the time diagrams that some of you will be familiar with. So in this social interaction, Alice decides to have dinner. And then she tells that to Bob, and Bob agrees to have dinner. But meanwhile, there is a third party, which is Chris, that is bored, he has nothing to do. And finally, he hears about the dinner plans, and he asks to join. So this is a social interaction, and now let's see it in the space-time diagram. So in order to track these things, we are going to assign unique event identifiers to each action. So when Alice is asking if someone is interested for dinner, we tag that thing with the A1. So to do that, and we often call this thing a dot, this unique track, what we need is a location name. Here it is Alice, and I'm just using the A letter. And we have a monotonic counter, so a counter that is always growing that we can use in a single location to distinguish different events. So I'm using 1, 2, 3, etc. And we do these things in the several locations. So now we can talk about events, and the arrows show message passing, the arrows between locations. I also included a timeline. So this is what will be global time if such thing existed. So a global view of the system. So one thing we can see here is that there are events that are actually concurrent. So the fact that Alice is wanting to have dinner is unrelated to the fact that Chris is bored. So this means that Alice didn't influence the state of Chris in the event C2, and the fact that Chris is bored did not cause Alice to want to have dinner. But if we look at this thing under real time, if we think that real time is the solution, what we will see is more relations that actually exist. So in real time, Alice wanting dinner was before, in real time, than Chris being bored. So it might look that it could have influenced. But what we actually know from what information went through the system is that these two things are not related. So actually causality brings us more information about what's happening than what is brought by real time. So how are we going to track this? We cannot be drawing arrows all the time in the system. So we could go and check the vector clock entry in Wikipedia, and you get all these nice formulas over there that will tell you how to use vector clocks. But this is a little bit complicated and magic. So nowadays, lots of people need to use these tools, and they just go, they check the rules, and the rules kind of work, or they use a library, but this always looks a little bit kind of magic. So I will try to give you some intuition of how these rules are like that, and where do they come from. And to that end, we'll start with something simpler, call it causal histories, which was a concept introduced in 1994 by Schwarz and Mattern. And I'm going to show you what these things are. So the basic intuition is, again, that we are collecting memories of the events that we have seen in the past. And we do that by simply by collecting a set of events. And if we have unique event tags, dots, and if we collect sets of events, we can use set inclusion to explain causality. So if I know something about an event, I must see all the events that is registered with it. If I don't know, if me and another entity, if we don't know each other's history, then we are concurrent. And if our histories are the same, we are the same. So let's put this into the social interaction that we had there. And here we are doing two things. We are assigning the events and we are collecting the sets of events. And now we can use this information to see what is happening in the graph. So if we look at the first reception of a message in node B, we are receiving the message A1, A2, the set of events are coming with a message. We receive it when we were at state B1 in node B. And basically what we do is that we merge the two sets. And after merging the two sets, we know our past. But since we have to register the receive event, then we need to create a new tag, the B2 tag, and union that. So this is what's happening in this flow over here. So I hope that everyone is getting this interaction here. We are just collecting sets of things and comparing sets of things. And this is where we do the causality checking. So we just see for set inclusion. So if we have set inclusion, then we have an event that was a predecessor of another event. But we still, well, checking set inclusion, I'm going to show you a little trick, is a more or less complex operation because you have to compare the two sets. So we can do a little trick. If we take note of the last event that, sorry, this thing is getting out of position. Okay, it's okay. So if we keep track of the last event that we have over there, we can do it much more simpler. We simply see if the last event is present in the set, okay? And this will give us the same information, because if we have the last event, we must have all the other events that come with it. It should be better now. Okay. Okay. So basically what we did is that we use this property that if we have the last event, then we must have all the other events, so we don't have to test the whole set. And there is another property over here, is that if we have a given event in the history, say if we have C3 over there, this also means that we need to have C1 and C2. So actually these histories here have a lot of redundancy. And this is why these things are not used in practice. So how can we do better than this? Well, we can use vector clocks, which were the structures that I shown in the Wikipedia entry. So vector clocks were created concurrently in 1998 by two researchers, by Fitch and Mattern. And they are used in many subsystems nowadays. For instance, to do group communication, to take a snapshot of a system. They are really basic building blocks. So how do we get from causal histories to vector clocks? Hoping that you got intuition into causal histories. So we have all these events over there, and we are going just to take note of the last event from each location. So from location A, we are only interested on the number 2, on location B on number 3, and on location C, also on number 3. So we have this map from location to a natural counter. And we could use this. This is actually what is used if the system is dynamic and we have many places that are not necessarily consecutive. But if we have the lack of having places that are consecutive, just like A, B, and C, then we can simply put this thing into a vector. We just make implicit the location names. So this is what a vector clock looks like. So it's only a compression of a causal history. So now, if we put this thing back into the diagram, we have this interaction here, and I'm going to show how we can read the interaction. So when we are receiving a message, again, the receive event at node B, what we are receiving is the vector 200, and we need to merge it with the vector that we had, 010. So what we do is a pointwise maximum for each of the coordinates, and the result of that is what we are going to use to increment the counter associated to node B. So we do an increment on B in the end, and we get the end result, which is 220. So this is the basic mechanics. To do the causality check, before we did checking of inclusion between causal histories, now what we do is we need to pointwise or coordinate-wise check if each coordinate has the corresponding value in the other coordinate is greater or equal than it. So I've assigned it some colors to make it easier. So we basically, to check these two, we need to check 2 with 2, 0 with 2, and 0 with 0. And since it happens in all the cases, then there is a causality link between the two. So can we make it faster, that trick? So this trick is not very well known, so this is a new thing, more or less. We can, again, do the trick that we did before with the last event, but this time we need to put it in bold over there. That 2 in bold means that that was the last event from replica A, and we just need to test if it is known on node B. So it's not very easy to code bold stuff and arrows in a programming language, so we need another way to encode this thing. So we can do this little trick where 200 will now be decoupled. We can decouple the last event and store it outside. So now, what we have is the causal path of, so for event A2 now, we have the causal path of it, which is 100, very compressed, and we store the event itself outside, okay? We call that thing a dot. And we do the same thing over there for that vector. So we could do these things for each vector as long as we do it when we are producing it. And now, how do we check? Well, we just go there, we pick the dot, and we see if the dot is known on the other vector, or the index is known in the corresponding position in the other vector. So what was a linear operation in the number of elements in the vector, now it's probably a constant time operation. Okay? So up till now, we have been registering all the events that are occurring. Okay? So we are registering internal events, send events, receive events, etc. But for some systems, it's not important to track all the events. So we might be interested, and in very practical systems, we are typically interested in only tracking events that change data. So vector clocks can be used for instance, for causally ordered message dissemination, but we are going to track only some events in order to get into another notion, which is a version vector. And in this case, we are interested on change events. So this has applications in file system, databases, and version control. And I think that probably everyone knows about this motivating example. So in the Dynamo paper that describes the Amazon shopping cart system, what they are doing is that they are tracking the events that change the shopping basket that is being managed. So every time given user is, or some proxy doing operations on his behalf, are doing operations to the shopping cart, what is written is tagged with a vector. So we are keeping track of all the right operations, but we are not worrying about sending messages, etc. So what does it look like? So to understand it, we need to get back into the causal histories. So now we have this distinction between the events we are interested in, which we are marking with a dot, and we put a dot because those are the events where we need to put a unique tag. And the other events that we don't need tracking. So for that one, those ones we use an empty circle. So in this case here, we have two write events, one at node A and another at node B. But then when we send a message, at that point, we are just propagating information. So what are we talking about here? We could be talking about a document and a shared editing. So these kind of things need to be used in things, plus other technology in things such as Google Docs. So we can be editing a document, and node A is writing a given line, and node B is writing an alternative line, another line. And when we propagate information, we need to merge these into a single document. So we need to realize that these things are concurrent. And this is really easy to realize because one is not included in the other, and neither happens vice versa, so they are concurrent. And when you receive concurrent things, we typically need to ask the user for a reconciliation. Okay? So this is what happens in a version control system when you have a merge conflict. We ask the users to do something. And since the user is doing something, the decision or what we write back needs to be tagged with a new event, because two different users can do different reconciliation decisions. So we need to tag that. So this is what happens over there. In that case, we had concurrency, and we also, the last interaction over there is just that we are sending information to a node C that was in an empty state, so with a blank page. In that case, it's very easy to see that this information at node B overrides the information on node C. So we can simply overwrite over there after doing the test. So when we do the causality test here, we can either, there is concurrency and we need user intervention, or some copy is outdated and we simply overwrite it. We can do another trick that actually happens in some databases, and that is, again, think about the Dynamo case. This also happens in the React database. Sometimes we don't want to do the reconciliation when we are handling the writes, because it may take some time and we want to give a fast response to the write. So we might want to have two copies at the database when we have concurrent writes. And this is what happens here. We will have two copies of the state. One is characterized by this causal history A1, and the other alternative one that has the other alternative line is by causal history B2. And we can defer, so we have two siblings over there, two states, and we can defer the reconciliation of the states to a later phase. For instance, these things sometimes are done at the read phase, such as in React. And at that point, we typically have to register a new event to mark the reconciliation. And the rest of the run is just the same thing. So that was the intuition with causal histories. Can we do the same thing in a compact way? Yes, we can. We can do it with version vectors. That, interestingly, they were invented before vector clocks. So this is a paper from 1983. This is a very visionary paper, so I recommend everyone to read it, even regarding things like cap, etc. So this is the run when we look with version vectors. As you see, we only increment values when we have those bullets there, and we are just passing out information in the system. So in the end, we have a 120 that is more recent than 000, so we just overwrite information over there. So I think this one should be clear by now, giving the previous slides. And sorry, I'm missing one slide here. Okay. We can also do the same trick in the case of version vectors, if we store the last version outside. So I'm coming to the end of the talk. In the last 30 years, there were a lot of causality mechanisms being developed. Some of them are useful, some of them are not so useful. There are libraries for some of them. But all of them can be translated into this simple notion of a causal history where you have the events that you are interested in. So basically, causality is important because time has limitations. So it might look that the fact that you are ordering everything is the best scenario, but actually by ordering everything, you are losing information. So you actually have more information if you store the partial order, the causal relationships, than if you try to order everything. Because what is happening now in Australia is not influencing what we are doing here. Okay? The other thing is that to track causality, we need to memorize events. And the simplest way is just to collect sets of events. So that was the basic building mechanism. However, these things, although they are very simple encodings of causality and they give you all the information that you need, they are highly inefficient. So we cannot use typically causal histories in practice unless we were dealing with a system where very, very few events are those that are of interest. So if we have enough events, we cannot use those things in practice, so we need to use practical mechanisms. And these practical mechanisms include vector clocks, version vectors, dotted version vectors. And what they are doing is simply doing an efficient encoding of causal histories. They are not adding extra stuff. They are just efficient encoding. So most of the causal mechanisms are like that. And when we look at the rules for comparing vector clocks, what we are seeing is that just the set inclusion being mapped into the representation that the given mechanism is using. Nothing more than that. So my takeaway thought on this talk is that when you are faced with a need either to design a new mechanism or to understand what kind of causality tracking you need to use in your system, you should try to think how that thing tracks back to a simple causal history, understand the problem in terms of causal histories, and anything else is just a coding strategy. So most of the content here, for those interested, is also in an article that came in ACMQ. This one is freely available. There's also a version that came in Communications of ACM in April about this, so you can follow through on this information. And these are my contacts, okay. So thank you, I'm open for questions.
Any question? Thanks a lot.
Okay. Oh, there's a question over there.
Oh yeah, wait.
Time for lunch.
Since there aren't any other questions right now, this one is more philosophical, but during the talk, which I found very interesting, I found it hard to get my head around you using the word causality. And maybe you can share an intuition about that. To me, it seems like saying your entire history is the cause of what's happening now is not informative enough in a way. So how do you pick the things that are really the cause?
Okay, so you are right. So we are actually talking about something more precise, which is potential causality. So not necessarily causality. So you are potentially influenced by everything that happened before you and that you are aware of. Okay? So this is the baseline of what you can do. But we know that we are not influenced by everything that happened in our lives. We are just influenced by the events that we memorize that happened before us. So actually, in some systems, you can try to restrict the events that you register as potential causes to what we are doing. There's a paper called Bolt-on Causal Consistency that explores a little bit of this. Okay, but in the end, if you can encode all this information just in a version vector, that is something that has interesting scalability properties if you don't have lots of nodes, then that might not really be a problem. But otherwise, you are correct. So if you can have more semantic information in your system that tells you exactly which events you need to track, you can do better. You can even track less events and with that have more information because you are only considering the relevant events to what you are doing.
Could you please make some practical examples of this? Because, well, for me this sounds really interesting, but I'm striving to imagine how these can be applied, well, in my day-to-day engineering job.
Okay. So I'm going to use an example that I know more or less, which is from the RIAC database, so from Baquero. So they do kind of an implementation of Dynamo with most things in common, some variations. So it is a NoSQL database with a get-put interface. And they want to be always available. And they typically, in the mode that I'm concerned with, they don't do coordination. So users can go and fetch an object through a get, then do some change to the object, and then put something back. So what happens if two users get the same object and do concurrent changes? You have two options. Well, we have more than two options, but you can use something like last writer wins, where a user puts the information there, and when the second user comes, it will overwrite information. But this is actually not correct, because the update that was done by the first user is as important as the update that was done by the second one. It just got unlucky with the timing. So databases that use last writer win, when these things occur, they are losing information, and this information can be important. So what they do in RIAC is that when these things happen, they store two siblings. So they recognize the fact that it was a concurrent interaction with the system, so you have two copies of the data, and they need to somehow know that they are siblings, and they can use version vectors for that, and now they are using a more complex thing, which is dotted version vectors to track that, because of scalability concerns. And what you have when we have two siblings, now the next user that is going to read the database will get these two copies, and the application layer has a chance to do the reconciliation of the copy, and then write back. So these things can be used in this context to don't lose any update. And doing the reconciliation at the application level can be hard, but you can also use another technology that I'm working with, which is conflict-free replication, replicated data types, where you can try to remove the burden of the reconciliation from the application and just use libraries that know how to reconcile sets, reconcile sequences, counters, etc. So this is one of the practical uses of these kind of techniques.
So,
Thanks.
thanks a lot.